Hello, today is June 18, 2024. We're going to continue about the electromagnetism. We're going to continue talking about electric potential energy. Okay, so today we're going to talking about the potential energy due to 2-point charge. Let's say this is a charge QS, which means the source. This will be charge Q0, which means the tested charge. Both are positive. So we know the electric field due to the source is going to be like that, right? So the direction of E is that. And then if we place the Q0 or Q0 over there, then since both are the same polarity, so the charge is going to move in that direction, Q0. And then let's say if the starting position we call it A, and then we move radically. When we say radically, we means we connect those two and then extend it to point B. We want to look at the work from point A to point B. Again, the work from point A to point B is going to be the integration from point A to point B. Inside will be the force, the electrical force, the dr, right? Dr with the path from point A to point B. And then from the previously discussion, we know the electric force F, that will be K times the 2Q, right? So it will be QS times Q0 divided by R squared, where R is the distance between those two. And then dr. Technically, we should also have cosine theta, where theta is the angle between the electrical field E and the actual path, which is from A to B. But since both are pointing to the same direction, so the angle actually is 0. So this part is gone, since cosine 0 equal to 1, when times 1 is going to be the stuff itself. And then here, before we go further, I want to do a quick review for the integration. So if we have an integration x to the power of the n dx, that actually equal to the exponent right here plus 1 as the denominator. The numerator will be x to the power of n plus 1. This I'm not going to derive here because that will take too much time. I'll put it like that. You can treat it this as the formula, and then if you don't know how to get this, you need to review your calculus book to figure out why it shouldn't be that hard. It's relatively easy. Okay, so with that being said, here K, QS, Q0, they are constant, so we can factor them out. QS, Q0, and then integrate from A to B, R to the power of the 2 when 1 over it, right? We can write it as R negative 2 dr, and then this part is gone. And then we apply this formula right here, we will get a K times QS Q naught, and then this will be N in this case is negative 2. So here negative 2 plus 1, and then it will be X N plus 1. In this case will be R, negative 2 plus 1. So negative 2 plus positive 1 is negative. We put it right here. So use negative K QS Q naught times, this will be R to the negative 1, right, which is 1 over R. And then we are going to integrate from point A to point B. Again, here's point A to point B. And then that will be negative K QS Q naught. We plug in this one first, subtract that, so you 1 over R A, subtract 1, RB, because this is the ending point, subtract RA. Okay, so if we use the distributive law to move the negative sign inside, we will have K, we will have K QS Q naught 1 over RA subtract 1 over RB. And then we can further use the distributive law one more time. We will get a K QS Q naught over RA subtract K QS Q naught over RB. Right? Remember last time when we're talking about work from point A to point B, that is equal to potential energy at the point A, starting point, subtract potential energy at the ending point. So notice this A matches that A, this B, that B. So the potential energy can be defined as K QS Q naught over R. Right? So this is the important formula you need to memorize it, because this tells you the point charge, how do you calculate the potential energy. And then even though we derive this through the more special case, in general, if we have a QS, right, and then let's say the QS electric field like that, right? If let's say this is the start point A and then ending point B right here, and then if we just use the random path from point A to point B, this still holds. Why? Because each of the little paths you can decompose into two components. One is perpendicular to the E, another one is exactly the same direction as the E. So the one perpendicular of E, the angle theta, will be 90 degrees, right? When you apply this, cosine 90 degrees will be 0, then the whole thing is gone. So what you left is the components that's in the same direction as E, which is indeed this case. So what I try to say right here is, even though we derived this from the special case, but it applies to the general case as well. Okay. Another thing I want to tell you is, what if we have 3 or even more than 3 is the source? Let's say this is the QS1, this is the QS2, and then this is QS3. if we try to find the potential energy right here due to those three, how do you do that? You basically connect those three. Let's say this is your R1, R2, and R3. You use the exactly same formula to calculate the U sigma, which is the U sum, which is U1 plus U2 plus U3. And then that would be K, QS1, Q0, R1, actually it's Q1, plus K, QS2. You know what? The testing right here, it is indeed a Q0. If this, we have a Q0 right here. The Q0 2, and then plus K, QS3, Q0 3. And then all you need to do is add those together. Okay, so now I'm sorry, I forgot to move the paper, so again, let me repeat one more time. So this is everything what we derived before, and this is what I said, we just review, and this is the equation for the potential energy. Again, let me repeat one more time. If it is a random path, then each path can be decomposed into two components. One is perpendicular to E, one is exactly same as E. So if it's perpendicular to E, theta is 90 degrees, so this bar is gone. So even though it's a random path, the only component that matters is the one has the same direction as the electric field E. So we should go back to here. So another thing is, if we have multiple charges, we just use the same formula multiple times, and then we add those results together. Okay, so now there's another thing I want to share with you guys. So let's say we know this is the, let me write it one more time, U equal to K QS Q0 over R, right? What if I want to draw the graph, which the y-axis is the R, is the distance, okay? And then is this distance right here, okay, the distance. And then U would be the potential energy, okay? So in this case, how do you graph this? Let's say we have a positive Q as the south, and then another positive Q now as the testing, right? So let's say if we don't do anything, right? If we just put a positive charge right here, since they have the same polarities, the electrical force acted on Q naught due to QS is in that direction, right? So that force will push this charge go all the way into infinity, right? So here the U is the potential energy. We know the U equation is like that. We can tell this. As R is very small, when you, all the rest is constant. Constant divided by a small number, the whole thing is a huge number. So when R is small, it's very large. As R increase, when you divide it by a larger number, your value becomes small. So the graph is going to look like that. So you shouldn't ever give up. Rest up. You should always like that. You will be very close to R but never touch R. Eventually you are towards something had zero potential energy, right? On the other hand, if the QS is a positive, and then the Q naught is negative, let's say after we push all the way to the infinity, and then we replace this with the negative charge. So the negative Q naught will go all the way here's negative, go all the way to the positive. Why? Because they have different polarity, they're going to attract each other. So if I want you to graph, that will be from infinity go all the way to a negative potential energy. So this is very important. Okay, so you might already be familiar with the gravitational potential energy. You know, when you say you got a kind of like slope like that, you have a ball right here. The ball will automatically rolling to the valley of the little hill, right? So that would be similar to something right here. But here, this part right here, you have to kind of use your imagination, right? So it is a little bit hard to imagine something in real life. You can see that, right? But you can kind of view it as the following. It's as another kind of slope. It's not strictly slope. It's kind of like a curved slope. And then the ball starts at the zero potential energy, and then they keep sliding down until another value. And then compared to this is going to be a negative value. Again, this is something to try to help you to understand this. Again, when we're talking about the electric potential energy, you must understand this graph. So the top one is when the polarity is the same, and then the bottom one when the polarity is different. I hope that help you a little bit to understand the electrical potential energy. Thank you again, and please feel free to let me know if you have any questions. Talk to you later. Bye bye.